Okay, in this video we're going to look at creating graphs for all 6 of our trig functions, and we're going to start with sine and cosine. And so when you're looking at this unit circle, remember what you have is you have angle values all the way around from 0 to 360 degrees, or in our case 0 all the way around to 2 pi radians. And for every single angle value we have a terminal point based on this angular rotation, and each terminal point gives me an x and a y. Well, each terminal coordinate, the x value represents the value of cosine, and the y value represents the value of sine. So what we're going to do is we're going to unwrap this unit circle, and we're going to use the radian value and the associated cosine value, or the radian value and the associated sine value, to create one full wave of sine and cosine between 0 and 2 pi radians. And so what we have here is, here on the left-hand side, remember cosine represents the horizontal displacement from the center of the circle, or in our case it's going to be all the x values of the point. So what I've done is I've gone all the way around the circle from 0 all the way to, no, technically 2 pi would be back where I started, so 0 through 11 pi over 6, and I wrote down the associated cosine values, which are all the x coordinates. And I did the same thing for sine, because sine represents the vertical displacement from the center of the unit circle. And so I have all of my radian values here in black, and then sine's values in red right here beside it. So what we're going to do is we're going to take the radian angle measures, and the angle measures are going to become the x-axis, and the corresponding output of cosine and sine are going to be the y values of the curve. And if I take those radian values from 0 all the way to 2 pi and put them on a horizontal axis, and then start plotting the values of cosine and sine. And so cosine is here on the left. And I'm just placing where they be. So like cosine of pi over 6 is 3 pi over 2, and then so forth. And what you'll see here is, if I connect these dots with a nice smooth wave, I'll create one full period of cosine. And I have it colored by quadrant, and the same thing with sine. And so I take all of sine's outputs for this corresponding radian values, plot those points as I work my way from the left to the right, and I can see one full graph of sine. Now we've seen the general behavior of a sine and a cosine wave. In fact, they look very similar to one another. They both have the same kind of behavior. Now what we want to do is we want to identify some vertical and horizontal features, and we'll start with our horizontal features. And the main horizontal feature that we have is the period. Now the period is the displacement along the horizontal for a graph to complete one full cycle. Period is always a positive measure. So we got to figure out, well, what dictates a full cycle? How do I find the period from a graph? There's a couple of ways of doing it. And so if I zoom in here on this graph on the left-hand side and try to figure out ways to find the period. Well, if I look here at the start to a finish and figure out, well, how much of this graph would I need to trace in order to do everything this graph's going to do? So I would start at the midline, or that place right there at 0, and I'd keep tracing until eventually, once I get from here, I've done everything this graph's going to do, and I'm going to start repeating myself. So that would dictate one full period. These points here, where the cosine wave or the sine wave is in the middle of its values, are considered to be the midlines. So all of these points here are the midlines. One full period is going to be the distance between 3 midlines. So 3 midlines is equal to one full period along the horizontal. Now, there's another way that I could look at this and define my period. So let me erase that part that I traced. What if instead of starting at a midline, I started at a peak? So let's say I go from maximum to maximum. If I trace that section of graph here and look at that piece, if I go anywhere outside of that part in purple, we're going to repeat everything that the graph had already done. And so the distance from max to max is also equal to one full period. So we have a couple of ways. So the horizontal displacement from identical peaks, or 3 consecutive midlines will get me my period. And our vertical features, we've already talked about one, is we have the midline, which is the middle value of the sinusoidal function, just means the middle y, or the average y value. And then we also have the amplitude. Amplitude is the maximum displacement from the middle to a peak. Amplitude is always positive. So graphically, if I wanted to know what amplitude was, let's say I have my maximum here, and then we have our midline here in green. Amplitude would be how far do you go from that max to get to a peak, call it A. Or excuse me, how far do you go from that midline to the maximum, or how far do you go from the midline to a minimum? Either way, that same displacement is your amplitude in either direction. Now the general form of sine or cosine, the equations are written right here. Now these letters, the A, the W, the H, and the K, they're interchangeable. I could use A, B, C, and D if I wanted to, but their effect on a graph is what I need to know. So A stands for the amplitude, also known as the vertical stretch factor in terms of function transformations. K is my midline, which is the vertical shift, moving up or down one or however many units for my graph. H is the horizontal shift, but in terms of our sinusoidal functions, we call that the phase shift. So our horizontal translation is also known as our phase shift. Now W is our horizontal stretch or shrink factor. Now what that is, I need to know that because let's go back to the sine or cosine wave here. Now I showed you how to find the period. Max to max are 3 consecutive midlines. Well, if I wanted to know what was the original period of a sine wave or a cosine wave, find the distance here in between the two maxes. So I go from 5 pi over 2, from pi over 2 to 5 pi over 2, the period from start to finish is 2 pi radians. So if I don't compress horizontally or expand horizontally a sine or a cosine wave, the period should have been 2 pi radians. Now, what that means is, if I change W in my equation, so I make it a number, to figure out what my horizontal stretch or shrink factor is, I take W, and then to determine my new period, I do 2 pi divided by W, and that's going to tell me what my new period is. So that way in my mind, if I know this number is bigger than 2 pi, I expanded it, and if it's smaller than 2 pi, I compress this sine wave or cosine wave. Now, the domain of sine and cosine is the set of all real numbers. The range here, if I look, it's bounded in between two y values. Our normal sine and cosine wave would be bounded between -1 and +1. But in terms of just a general form, it's the midline. The minimum value is going to be midline minus amplitude, and the maximum value will be midline plus amplitude. Now let's look at graphing the reciprocal functions of sine and cosine, and that takes us to cosecant and secant. The reciprocal of sine is the cosecant function, and the reciprocal of cosine is the secant function. And so we'll start here on the left-hand side. The reciprocal of sine being cosecant, so that means cosecant is 1 divided by sine. Everywhere that sine equals 0, cosecant is going to be undefined, meaning it has a vertical asymptote. So on this sine wave that I already have plotted here, everywhere it crosses the x-axis or intersects its midline, its cosecant will be undefined. So at -2 pi, at pi, 0, pi, and 2 pi, cosecant has vertical asymptotes. I also know that wherever sine of x is equal to positive or -1, cosecant of x is also going to share that point because the reciprocal of +1 is +1 and the reciprocal of -1 is -1. So at all of the peaks of sine, cosecant is going to share those points. So I have those indicated in purple. So at -3 pi over 2, pi over 2, negative pi over 2, positive pi over 2, and 3 pi over 2, cosecant shares those values. Now, to get the sketch of cosecant, cosecant does not have any x-intercepts, so I would go at those peaks and I would turn it away from the midline in both cases where it has unbounded behavior. in both instances. And so since I have to exclude all of the whole numbered pi's from here, our expression for our domain would be all real numbers except for pi times n, where n is an integer, meaning I'm putting in positive or negative whole numbers for n, and that would generate all of these vertical asymptotes. Our range for cosecant would be the set of all real numbers except for going in between -1 and +1. So the way I would write that would go from negative infinity to -1, inclusive on the -1, and then 1 to infinity, and I also include that 1. Now let's talk about the period. So how far along the x-axis does it take for cosecant to repeat itself? Well, if I look, it's going to repeat itself every 2 pi radians. So the distance in between 2 maxes, or 3 of these vertical asymptotes, dictates 1 full period, and that's all 2 pi radians. Now let's look at the graph of cosine and secant. Cosine and secant are reciprocal functions. So if I wanted to create the graph of secant, I need to think of it in terms of cosine. So everywhere cosine equals 0, secant's going to be undefined because it makes division by 0. So everywhere cosine intersects its midline at all of the half-numbered pi over 2's, or all the half pi's, excuse me, that it is going to have secant being undefined. So I have vertical asymptotes at all of my odd-numbered pi over 2's. Everywhere that cosine equals positive or -1, where it has its maxes or mins, secant's also going to have a relative maximum or min because they're going to share that point with each other, and so they have those points in common. Now to finish the sketch of secant, just like we do for cosecant, secant has to turn away from the cosine function, or it cannot have x-intercepts in this case, and so I turn it away from where cosine would be graphed. Now the domain of secant would be the set of all real numbers except for where cosine equals 0, because that's where we have our vertical asymptotes. So we're going to write an expression for that. So the domain would be the set of all real numbers except for, it would be the pi over 2's, but it's a little trickier to write this one because it's odd number pi over 2's, -3, -1, 1, 3, and the next one be a 5. So that'd be pi over 2 times 2n minus 1. That'll generate odd numbers where n is an integer. The range would go from -infinity to -1. I include the -1. And then it would pick back up at +1 and go to infinity. And our period here is also 2 pi radians. So the period of sine and cosine and the reciprocals are all 2 pi radians unless I do some kind of horizontal stretch or compression. The general form of cosecant and secant looks very similar to that of sine and cosine. The main difference is that technically secant and cosecant do not have an amplitude. Even though I use the same letter, they don't have an amplitude because amplitude is defined as the maximum displacement from the midline. Since secant and cosecant technically don't have maximums or true minimum values, I can't identify the A as being an amplitude. Instead, we're going to let A be indicative of a vertical stretch or shrink. K is going to be our vertical translation, which would be the midline of sine or cosine. And then we have our horizontal stretch or shrink factor of W still. And we defined a period from an equation. We would do 2 pi divided by that horizontal stretch or shrink factor of W. Okay, now let's look at how we would graph tangent and cotangent. Remember that tangent is the quotient function of sine divided by cosine. And so I'm going to, just like we did with secant and cosecant, we're going to form the graphs of tangent and cotangent by looking at the graphs of the two functions that comprise them. So tangent's on the left-hand side here. So tangent is equal to the quotient of sine being divided by cosine. So I have this color coordinated here. The sine wave is in red. The cosine wave is here in blue. Now, since tangent is a quotient function, I have a function in my denominator. So cosine being in the denominator, everywhere that cosine equals 0, tangent's going to be undefined and have a vertical asymptote. So cosine being blue, Cosine equals 0 at negative pi over 2 and positive pi over 2. Cosine equals 0 is at all the odd numbered pi over 2's. So I go to my tangent sketch here, and all of my odd numbered pi over 2's get vertical asymptotes. Tangent is going to equal 0 where the numerator equals 0, and that's going to be where sine equals 0. And that's going to wind up being a point of inflection. So everywhere sine equals 0 here in red, all of my whole number pi's, I'm going to put dots on my x-axis for tangent because tangent's going to go through that point. And now we have to sketch the rest of the graph. Well, to sketch the rest of the graph, we're going to look at where sine and cosine have the same value. So where sine divided by cosine equals positive or negative 1, that's going to be where tangent gets to apply its vertical stretch factor, which is going to be halfway in between the point of inflection and the vertical asymptote. Now, in fact, we should know this because on all the pi over 4's graphically, at positive pi over 4, negative 3 pi over 4, and they even have the same value, but just opposite signs at positive 3 pi over 4 and negative pi over 4. So that's going to be where tangent equals positive or negative 1. I put those points here in purple. So that way I get some more points to sketch the curve. Tangent is a increasing function on its domain. So as you work your way from left to right, it should be increasing through here. And it resembles that of a cubic function, but it's not actually a cubic function. Now, the domain of tangent, notice how it's undefined. Tangent has a domain that's a set of all real numbers except for where it's undefined at, which is where cosine equals 0. Since cosine equals 0, depending on what, if we don't restrict the domain, we want to write an expression that would represent everywhere that cosine equals 0. Cosine equals 0 on all the odd numbered pi over 2's. So a way I could write this domain would be the set of all real numbers except for pi over 2 times 2n minus 1. That generates the set of odd numbers times pi over 2, where n is some integer. The range of tangent is the set of all real numbers. Look inside here in the middle. Every single y value would be accounted for in between those two vertical asymptotes. So the range is all reals. The period of tangent is not 2 pi. Look at how long it takes to do one full graph here. In between the window from negative pi over 2 to positive pi over 2, tangent does everything it's going to do before it starts to repeat itself. So tangent has a period of pi radians. Now let's go look at a graph of cotangent. So looking at the graph here of sine and cosine, also color coordinated. Sine is still red, cosine here is in blue. Cotangent is the quotient function of cosine divided by sine. So the first thing you do when graphing cotangent is figure out what makes it undefined. The cotangent is going to be undefined everywhere sine equals 0 because that's going to make the denominator 0. That's where it's going to have a vertical asymptote. So sine is equal to 0 on all of the whole number pi's. So negative pi, 0, 1 pi, 2 pi, and so forth. So I put vertical asymptotes there. Everywhere that sine equals 0, cotangent has a vertical asymptote. Everywhere that cosine equals 0, so everywhere that the top equals 0, cotangent is going to equal 0. So where sine equals 0, cotangent undefined. Where cosine equals 0, cotangent equals 0. So cosine equals 0 at all of at negative pi over 2, positive pi over 2, 3 pi over 2, and so forth. So all of the odd numbered pi over 2's, I put dots here because cotangent is going to pass through that point. Now we go get some other coordinates. We look at where cosine divided by sine is equal to positive or negative 1. It happens at all of the pi over 4's on our unit circle, and so I put those same points there on my graph. And then we connect those dots. Now, cotangent has the point of inflection everywhere that cosine equals 0. And if we look at the way the sketch has to happen with the unbounded behavior as we approach the vertical asymptotes, cotangent is going to wind up being a decreasing function on its domain. And on that domain, every single y value is going to be accounted for. So cotangent has a range of all real numbers. Now the domain of cotangent is going to be the set of all real numbers except for where it's undefined at. Cotangent is undefined on all of the whole numbered pi's. Now, since that's going to be where sine is equal to 0. So the domain of cotangents, the set of all real numbers except for where sine is equal to 0. The way I can write that as an expression would be all real numbers except for pi times n, where n is some integer. Like tangent, the period of cotangent, it only takes a window of pi radians for cotangent to do everything that it's going to do. You go outside of that window, it's going to start repeating itself. So cotangent, as one of my parent functions, has a period of pi radians. The general form of tangent and cotangent they look similar in terms of the constants being used to the other 4 trig functions. However, it's also important to note that even though I'm using a here at the front of tangent and cotangent, they do not have an amplitude because of the way we define amplitude. Since tangent and cotangent do not have a true maximum or minimum value, I can't say a represents amplitude. Instead, we're going to say a is the vertical stretch, k is going to be the vertical translation, but it's also the location of the y values of my points of inflection. So they don't have midlines, but they have points of inflection. They happen at whatever k is. The horizontal translation of my phase shift is still h, and our period is going to be pi divided by w. So we take whatever we're multiplying the input variable by, divide that by the period of my parent function pi, and that's going to be my period for the tangent and cotangent function.